Okay, so get this. We're diving into the science experiment.
Right.
And it's buried deep under a mountain.
Oh, wow.
It's designed to catch these tiny, almost invisible particles called neutrinos.
Right.
You know those super light, elusive particles that
Yeah.
are constantly streaming from the sun and basically passing through everything, even us?
Right. Neutrinos are fundamental particles, and they rarely interact with anything,
Exactly.
which makes them incredibly hard to study.
Yeah, so you've got this experiment called SAGE,
Hmm.
a Soviet-American collaboration back in the day,
Oh,
using liquid gallium to try and capture these neutrinos.
interesting.
But here's where it gets really interesting.
Okay.
They found less than they expected.
Really?
Way less.
Hmm.
This is the gallium anomaly, and
Yeah.
it's been puzzling physicists for decades.
It challenges our understanding of neutrinos and the standard model of particle physics, for sure.
Absolutely. We're talking about a 20 to 24% shortfall of neutrinos consistently across multiple experiments.
Wow.
Including GALLEX and BESRO.
Okay.
We've got research from all these experiments, along with articles from Wikipedia and Quanta magazine, trying to make sense of this puzzle.
So what are we looking at here? Like, what's the main takeaway?
Well, they weren't just looking at neutrinos from the sun.
Okay.
They were also using radioactive sources like chromium-51
Uh-huh.
to calibrate their measurements.
Interesting.
And they found the deficit in both cases.
Oh, so they had this backup source.
Yeah.
And they still couldn't explain the missing neutrinos.
Yeah, what did they think was going on?
Yeah.
Did they think they messed up the experiment somehow?
Well, that was the first thought, of course.
Right.
Scientists spend years trying to rule out any possible errors. They even considered whether they had miscalculated the half-life of germanium-71.
Hold on, germanium-71, can you back up and explain how this experiment actually worked?
Sure, the idea was to use a massive tank filled with 50 to 57 tons of liquid gallium metal, buried deep underground to shield it from cosmic rays.
To shield it from cosmic rays. Okay.
When a neutrino interacts with the gallium atom, it can produce a germanium-71 atom.
So they were counting these germanium atoms to measure the neutrinos. Clever.
Right.
But if they were missing germanium-71, does that mean they were missing neutrinos?
Exactly. The fewer germanium-71 atoms they found, the fewer neutrinos they knew had interacted with the gallium. But even after accounting for all the known factors, the deficit persisted.
Okay, so walk me through this.
Right.
What were some of the potential errors they considered?
Well, one possibility was that neutrinos were oscillating. You see, neutrinos can actually change flavor as they travel.
Neutrino flavors?
Yeah.
So they're not really flavors like ice cream, right?
It's just an analogy.
Okay.
The flavors refer to the three types of neutrinos: electron, muon, and tau.
Okay.
And as these neutrinos travel through space, they can actually transform into each other.
Wow.
It's a bit mind-bending, but it's a real phenomena.
So maybe the neutrinos were changing flavor and that's why they weren't showing up.
That's what they thought. But the best experiment,
Okay.
which was designed specifically to test for neutrino oscillations, used a two-chamber setup to account for this possibility.
Okay.
And they still saw the deficit in both chambers.
Wow. So they went to great lengths to rule out a simple explanation, and yet the anomaly persisted.
It did.
What about the half-life of germanium-71? You mentioned they thought they might have miscalculated that.
That was another possibility.
Okay.
But a separate experiment meticulously measured the half-life of germanium-71 and confirmed it wasn't the issue.
So that explanation was ruled out too.
Yes.
All right, so they checked the calculations, they accounted for neutrino oscillations, they ruled out errors with the germanium-71.
Yeah.
It really seems like they've covered all the bases.
They really did.
Where does that leave us?
This is where it gets really interesting.
Okay.
If it's not an experimental error, then what could it be?
Yeah.
This is what led some physicists to propose a radical idea.
Yeah.
Sterile neutrinos.
Okay, hold on.
Sterile neutrinos. What are those?
Sterile neutrinos are hypothetical particles that don't interact with the weak force, like regular neutrinos.
Okay.
They would only interact through gravity, making them almost impossible to detect directly.
Wow.
But if they exist, they could potentially mix with the known neutrinos,
Okay.
leading to the observed deficit in the gallium experiments.
This sounds pretty far out there.
It is.
Are physicists really taking this idea seriously, or is it just a fringe theory?
There's definitely a lot of excitement and interest in the scientific community.
Okay.
The gallium anomaly, along with a few other tantalizing hints, has led to renewed efforts to search for sterile neutrinos.
Speaking of those tantalizing hints, let's talk about another piece of this puzzle.
Okay.
The MiniBooNE experiment.
Yeah.
Didn't that experiment provide some evidence for sterile neutrinos?
Yes. The MiniBooNE experiment at Fermilab observed an excess of electron-like events that could be interpreted as evidence for sterile neutrinos. However, later experiments, like MicroBooNE,
didn't confirm those findings.
Oh, really?
So it's a bit of a mixed bag.
Yeah.
Some hints, some contradictions.
Right.
But the gallium anomaly remains a persistent puzzle.
So we have this anomaly, this possibility of sterile neutrinos. But if we can barely detect them, how would they explain those missing neutrinos in the gallium experiments?
That's where the concept of mixing comes in.
Okay.
The idea is that the electroneutrinos, the ones these experiments were primarily designed to detect, could be oscillating into these sterile neutrinos.
Okay.
And since sterile neutrinos wouldn't interact with the gallium, that would explain why less germanium-71 was being produced.
Okay, I'm starting to see how the pieces fit together, but let's back up for a second.
Sure.
You mentioned other tantalizing hints besides MiniBooNE.
Yeah.
What were those?
There's the reactor antineutrino anomaly.
Okay.
Some reactor experiments have detected fewer antineutrinos than predicted, which could also potentially be explained by sterile neutrinos.
So we have these multiple anomalies all potentially pointing towards the same thing, sterile neutrinos.
Right.
If they actually exist, what would that mean for our understanding of the universe?
Well, we've been talking about neutrinos.
Yeah.
But what's even more mind-blowing is that these sterile neutrinos could be a component of dark matter.
Dark matter?
Yeah.
I've heard that term thrown around a lot.
Yeah.
Can you remind me what it is?
Let's think of it this way. We can only see about 5% of the matter in the universe.
Okay.
The rest is dark matter.
Okay.
We know it exists because of its gravitational effects on galaxies and galaxy clusters.
Okay.
But we don't know what it's made of.
So 85% of the universe is this invisible stuff.
Pretty much.
And these sterile neutrinos could be a part of that.
They could.
That's pretty huge.
It is.
Wow.
And if sterile neutrinos are indeed a form of dark matter, it would be a revolutionary discovery.
Yeah.
It could potentially help us unlock some of the biggest mysteries in cosmology.
Okay, I'm definitely getting why scientists are so interested in this.
Yeah.
But some people might say this whole search for sterile neutrinos is a waste of time and resources, especially given those conflicting experimental results.
Right.
What would you say to them?
I'd say the pursuit of knowledge is never a waste of time.
Okay.
Even if sterile neutrinos turn out not to be the answer,
right,
the search for them could lead to other important discoveries.
Okay.
And think about it. If we do find evidence for sterile neutrinos, it would require a significant revision to the standard model of particle physics, our current best understanding of the universe at its most fundamental level.
That's a good point. Speaking of the standard model, how do these sterile neutrinos fit into that framework? Does it even allow for them to exist?
The standard model, as it stands, doesn't account for neutrino masses or dark matter.
Okay.
So if sterile neutrinos are confirmed, it would definitely need to be modified.
So it would need to be modified, okay?
But there are already some theoretical models that extend beyond the standard model and predict the existence of sterile neutrinos.
Can you give me an example of one of these models?
One example is the seesaw mechanism.
Okay.
Imagine you have a seesaw, and on one side you have a very heavy person.
Okay.
And on the other side, a very light person.
Got it.
To balance the seesaw, the heavier person has to sit much closer to the fulcrum.
Okay. I'm seeing where you're going with this.
In this analogy, the heavy person represents a hypothetical heavy neutrino, like a sterile neutrino.
Okay.
And the light person represents a regular neutrino. The seesaw mechanism suggests that the heavier the sterile neutrinos are, the lighter the regular neutrinos would be.
So it's a kind of balancing act.
Exactly.
The existence of heavy sterile neutrinos could explain why regular neutrinos have such tiny masses.
Right.
That's pretty elegant, actually.
It is.
Yeah.
And it provides a theoretical motivation for why physicists believe sterile neutrinos might exist.
Okay, so we have this anomaly, a potential theoretical explanation, and some tantalizing hints. But how do scientists actually go about looking for something that's so hard to detect?
Right.
What kind of experiments are they designing?
There are several approaches being explored.
Okay.
Some experiments are looking for direct evidence of sterile neutrinos by searching for their decay products.
Okay.
While others are looking for indirect evidence by studying neutrino oscillations with even greater precision.
Okay.
They're casting a wide net, trying to catch these sterile neutrinos from different angles.
Can you give me an example of one of these experiments?
Sure, let's take the example of the Katrina experiment in Germany.
Okay.
It's designed to measure the mass of neutrinos with incredible accuracy.
Wow.
If sterile neutrinos exist and mix with regular neutrinos, it could affect the measured neutrino mass, providing indirect evidence.
So it's like trying to detect a planet by observing the wobble of its star. Pretty clever. What about the direct detection experiments? What are those looking for?
Those experiments are looking for specific decay products that sterile neutrinos might produce.
Okay.
Like photons or other particles that we can detect.
Okay.
It would be like finding the sterile neutrino's fingerprint.
So we have experiments like Katrin looking for indirect evidence.
Right.
And others searching for their fingerprint.
Yeah.
It seems like these experiments are relying on some pretty advanced technology.
Absolutely. They're essentially building giant microscopes to study the subatomic world.
Wow.
Using incredibly sensitive detectors and sophisticated data analysis techniques.
It's amazing to think about the ingenuity and effort that goes into these experiments.
It really is.
But let's say they do find evidence for sterile neutrinos.
Yeah.
Would that have any impact on our everyday lives?
It's hard to say for sure.
Yeah.
The discovery of sterile neutrinos would primarily be a fundamental scientific breakthrough with major implications for our understanding of the universe. It's not like we'd be building sterile neutrino-powered cars or anything like that.
Right. No sterile neutrino smartphones anytime soon.
Exactly.
Okay.
But who knows?
Right.
History has shown us that fundamental scientific discoveries often lead to unforeseen technological advancements.
That is true.
Yeah.
So for now, it's more about expanding our knowledge of the universe than building new gadgets.
Exactly. And sometimes that's enough. Understanding the universe we live in is a reward in itself.
I totally agree. But let's get back to the gallium anomaly itself.
Okay.
Is there a chance that it's not sterile neutrinos after all?
It's possible.
Could there be another explanation that we haven't considered?
Of course, we should never rule out the unknown.
Yeah.
It's possible there's still some subtle experimental error that hasn't been identified yet.
What kind of error could have slipped through the cracks after all this time?
It's hard to say for sure.
Yeah.
It could be something to do with the detection efficiency of the germanium-71. Or perhaps there's some unknown nuclear physics process that we haven't accounted for.
Okay, so we're not ruling out a conventional explanation just yet.
Right.
But you also said we should never rule out the unknown.
That's right.
Are there any other more exotic possibilities besides sterile neutrinos?
Well, there are some theories out there, but they get pretty speculative.
Don't hold back. Let's hear them.
All right. Well, some physicists have proposed the existence of new forces or interactions that we haven't discovered yet.
Okay.
If such a force interacted with neutrinos in a way that we don't currently understand, it could potentially explain the gallium anomaly.
Hold on. Are we talking about a whole new fundamental force of nature?
Well,
like beyond gravity, electromagnetism, and the strong and weak forces?
It's highly speculative.
Yeah.
But it's a possibility worth considering.
Okay, so we've got sterile neutrinos, new forces, unidentified experimental errors. It seems like there's a whole range of potential explanations for this gallium anomaly. How do scientists even begin to sort through all these possibilities?
That's the beauty of science.
Yeah.
It's a process of elimination. Of testing hypotheses and seeing which explanation best fits the observations.
So it's like a giant puzzle.
Right.
And they're trying to find the missing pieces.
Exactly. And sometimes the most unexpected explanation turns out to be the right one.
Well, I'm definitely hooked on this mystery now.
Me too.
I can't wait to see what new discoveries come out of this research.
Hey, it's going to be fascinating.
But before we wrap up, I want to make sure we haven't missed anything important. You know, for our listeners.
Yeah.
Imagine you're explaining this to someone at a party.
Okay.
What's the one thing you'd tell them to make their jaw drop?
I think what's truly mind-blowing is this.
Okay.
We could be surrounded by these invisible particles, sterile neutrinos, that make up a huge chunk of the universe, and we're only just now getting hints that they might exist.
Wow.
It's like we're peeking behind a curtain into a whole hidden world.
Yeah. I'm trying to wrap my head around that.
Yeah.
So you're saying the reason galaxies behave the way they do,
right,
the missing piece in our understanding of the cosmos, could be these ghostly particles passing right through you as we speak.
That's the incredible possibility we're faced with.
Wow.
And it highlights just how much we still don't know about the universe.
It really makes you wonder what else is out there that we haven't even imagined yet.
Exactly.
To bring it back to the gallium anomaly.
Yeah.
What's the main message you want our listeners to take away from this deep dive?
I'd say it's this.
Okay.
Even the tiniest discrepancies in scientific measurements can lead to profound new insights.
Okay.
The Gallium anomaly is a testament to the power of careful observation and the importance of questioning our assumptions.
Right.
Sometimes the most unexpected discoveries come from paying attention to the things that don't quite add up.
Yeah, it reminds me of that saying.
Yeah.
The greatest obstacle to discovery is not ignorance, it's the illusion of knowledge. We think we know how things work, and then something like this comes along and shakes everything up.
Exactly. And it underscores the fact that science is a process, a journey.
Yeah.
It's not about having all the answers, but about constantly asking new questions and seeking deeper understanding.
Well, I think we've given our listeners plenty to ponder.
I think so.
Any final thoughts before we sign off?
Just this. The next time you look up at the night sky, remember that what you see is only a tiny fraction of what's really out there.
Yeah.
The Gallium anomaly is a reminder that the universe is full of mysteries,
Right.
and it's waiting for us to unravel them.
That's a perfect note to end on.
Right.
Thanks for joining me on this fascinating deep dive.
My pleasure.
It's been a real eye-opener.
I agree.
And to our listeners, keep exploring, keep questioning, and never stop looking up at the stars.
Absolutely.
Who knows what incredible discoveries await us?